Hello friends, I welcome you in lecture number 29 on hypothesis testing. In this lecture we are going to take an introduction of goodness of fit test. So what is the role of goodness of fit test? So far whatever lectures we have discussed related to hypothesis testing, in all those lectures we know that our population is of which type. We are familiar about the probability distribution of given population, and then we are doing different hypothesis testings. So up to lecture number 28, whatever hypothesis testing we have discussed, in those type of hypothesis testings the probability distribution of population is known in advance, and then we perform the corresponding hypothesis test. Now in goodness of fit test we don't know what is the probability distribution of given population. That is, we have probability distribution for population is unknown, and using the given sample data from that population we have to check that what will be the probability distribution of that population. So we can assume that our population follows this probability distribution, and under that hypothesis we can perform some test to check whether that assumed probability distribution fits to the given population or not. So the goodness of fit test helps us to test the hypothesis that given population has this certain type of population distribution. For example, from the given data we can assume that given population is binomial population, or given population follows binomial distribution, and using some goodness of fit test we can test that hypothesis. So that is the main idea of goodness of fit test. So for that you will be given a sample of some observations from that population whose distribution is unknown, and using that sample data you have to test the hypothesis about the probability distribution of that population. So in sample whatever data we have, that is called observed data, and we will assume that our population follows certain distribution, so that is called theoretical hypothesis. So we assume that our population follows this theoretical probability distribution. So using that theoretical distribution hypothesis we find out the expected frequencies by computing the corresponding probabilities, and then we check that whether these expected frequencies are close to the observed frequencies or not, and using some goodness of fit test we test that whether that population follows particular theoretical distribution or not. So that is the whole idea of goodness of fit test. The goodness of fit tells you if your sample data represents the data you would expect to find in the actual population. The goodness of fit test is used to test if sample data fits a distribution from a certain population, that is a population with a binomial Poisson or normal distribution. Goodness of fit test commonly used in statistics are these four tests: chi-squre goodness of fit test, Kolmogorov goodness of fit test, Anderson and Shapiro-Wilk goodness of fit test. In our course we are going to discuss only one goodness of fit test, which is called chi-squre goodness of fit test. So that goodness of fit test uses chi-squre distribution, and we have only this goodness of fit test in our syllabus, and this chi-square goodness of fit test is the most commonly used goodness of fit test. So that I have written here, the chi-square goodness of fit test is the most common of all the goodness of fit tests. So now we understand how to perform this chi-square goodness of fit test. So this is one type of hypothesis test. So our null hypothesis is always the hypothesis that given population follows certain probability distribution. That is always going to be a null hypothesis, and alternative hypothesis is that given population does not follow that probability distribution, and using certain level of significance we have to find out the value of test statistic. Now for given data we will be having a sample from that unknown population whose probability distribution is unknown. So we will have sample of say n observations. So we will have that sample data in this form. We will have different categories, and for each category we will have number of objects which lies or which corresponds to these categories. So we will have some frequency distribution type data. If our sample is given in terms of raw data, then we can make the frequency distribution from that ungrouped data, and we can prepare this type of frequency distribution if it is not given in the problem. Here we can write, instead of categories we can use all these different words. We will have different groups or classes, or we can write that another word is beans or class intervals. These are different words. So we will be having the number of objects corresponding to each category, and then we will have this type of frequency distribution. Now these frequencies from given sample are known as observed frequencies. So we will be given observed frequencies for each categories, and if we are not having this type of frequency distribution, then we can prepare that frequency distribution from this ungrouped data for sample. But generally they provide the sample data in terms of frequency distribution. Now this is the sample data from that population whose distribution is unknown to us, and we make the hypothesis that suppose the population follows binomial distribution. Then we know the formula for probability mass function of binomial distribution, and using that formula we will find out the probabilities corresponding to each value of that binomial random variable, and using that probability mass function formula we will be able to decide probability corresponding to each category, and after finding these probabilities we will multiply each of these probabilities by the total number of observations, and that will give us expected frequency for each category or each class. So that we have to find out for every goodness chi-square goodness of fit test. I repeat again, we will be given a sample of say n observations in terms of frequency distribution. We will have different categories or groups or classes or bins. If we have discrete random variable, we will have integer values for different categories. If we have continuous probability distribution, we will have class intervals or bins, and we will be given frequency for each category. So all those frequencies are called observed frequencies because they come from the given sample of observations. Now we want to check whether our population follows particular probability distribution or not. So we first assume that null hypothesis is true, and if null hypothesis is true, we have that population following certain probability distribution. So it will have formula for probability mass function of that distribution. Using that formula, we will calculate probability for each category, and after calculating those probabilities, we will multiply each probability by total number of observations in this sample, and we will obtain expected frequencies, which we will denote by capital I. Now suppose we have k categories, then for each category we will be having observed frequencies and expected frequencies. So after computing observed and expected frequencies, we will take the difference between observed and expected frequencies. We will square those differences and we will divide each squared difference by expected frequency, and this we will sum for all the classes or all the groups or all the categories. Suppose we have k categories, then we will have k terms of this type in the addition. So that is the formula for our test statistic for chi-square goodness of fit test. We will remember this formula: sigma O minus E whole square divided by E, and for all possible categories. So if I have 4 categories, I have to add 4 terms here, and here capital O is the observed frequency, capital E is the expected frequency. So our aim is to decide that how close these expected and observed frequencies are. So if this difference is small, then there are chances that our null hypothesis is true, and if this difference becomes large, then we will have large value of this chi-square test statistic, and there are more chances of rejecting the null hypothesis. Now after calculating this test statistic, we have to find out critical value for chi-square distribution. So for that we will require level of significance. If it is not given, we will consider alpha equal to 0.05, and we will require degrees of freedom also. So degrees of freedom are given by this formula, k minus p minus 1. Now what is k? K is the number of categories or classes. Suppose we have different groups or different class intervals, then that number of class intervals or number of groups are denoted by small k here. What is small p? So sometimes if we want to use probability mass function of a hypothesized distribution, suppose we assume that our population follows binomial distribution, then its probability mass function is given by ncx p raised to x 1 minus p raised to n minus x, where small p is the probability of success. Now suppose this probability of success is not known to us. Suppose it is not given. What is the probability of success for that binomial distribution is not given in the question. Then we will estimate this probability of success from the given sample data. So this small p is the probability of success for binomial distribution, and it is called parameter of the binomial distribution, and we are using sample data to estimate that parameter. So whatever number of parameters we have estimated using sample data, that is denoted by small p here. So suppose small p is the number of parameters estimated, number of parameters estimated from the sample data. if we have not estimated any parameter for the hypothesized population, then we will consider small p equal to 0. Suppose we want to test that our population follows Poisson distribution, then formula for probability mass function of Poisson distribution is e raised to minus lambda, lambda raised to x divided by x factorial, where lambda is the average number of events per unit of time interval. So this lambda is the parameter of Poisson distribution. Now suppose lambda is not given, then we will use sample mean as an estimator of that population parameter lambda. So in that case we are using we are estimating one parameter lambda from the sample data. We are using this sample mean to estimate that parameter lambda. So in that case we will consider small p equal to 1. So that is the idea of this small p in the formula of degrees of freedom. Small k is the number of categories or groups. Small p is the number of parameters estimated from the sample data. And using these degrees of freedom and this level of significance alpha, we will decide critical value of this chi-square distribution. Now once we decide critical value, we will check whether calculated value of test statistic, which is obtained using this formula sigma O minus E square divided by E. Suppose this calculated value of test statistic is bigger than chi-square alpha with new degrees of freedom. If this happens, then we are in rejection region and we reject the null hypothesis. Now remember that the critical values for this goodness of fit test, we are familiar with the shape of chi-square distribution. This is the rough sketch of chi-square distribution. So remember that for chi-square goodness of fit test, we always have right-tailed test. The chi-square goodness of fit test is almost always right-tailed test. Therefore, this chi-square critical value is always on this side, and this area is alpha with certain degrees of freedom. So what is the reason that this chi-square test for goodness of fit is always right-tail test? So the reason is in this formula. Suppose this difference is not small, or if this difference is more than expected, then there are more chances of rejecting the null hypothesis. And if this difference is very small, then we can say that observed and expected frequencies are very close to each other, and the chances of rejecting the null hypothesis are very less. So whenever this difference is big, we have this more chances of rejecting the null hypothesis. So we will remember that for chi-square goodness of fit test, we always have right-tailed hypothesis test, so that we will consider area alpha in the right-tailed test, and we will use chi-square table accordingly. So this is the procedure for chi-square goodness of fit test. I have written all these things which I discussed systematically here. A chi-square test can be used to test the hypothesis that observed data follow a particular probability distribution. The test procedure requires a random sample of size n from the population whose probability distribution is not known to us. The n observations in the sample are arranged into a frequency distribution with k groups or class intervals or bins or categories. Let O suffix I be the observed frequency in the ith class interval from the hypothesized probability distribution we compute the expected frequency in the ith class interval denoted by E suffix I. So to compute this expected frequency, first we have to compute the probability for each value of capital X, which is the hypothesized random variable, and then we will multiply this probability for each value of X by total number of observations in this sample. The test statistic is X naught square. Some authors are using this notation and this is also valid. So this is sigma I equal to 1 to k O suffix I minus E suffix I whole square divided by E suffix I, or you can simply write, you can ignore this subscript and you can simply write this as O minus E square divided by E, and this is our test statistic. Sum runs over all possible categories. If the population follows the hypothesized distribution, this X naught square or chi-square has approximately a chi-square probability distribution with k minus p minus 1 degrees of freedom, where this small p represents the number of parameters of the hypothesized distribution estimated by sample statistic. We would reject the hypothesis that the distribution of the population is the hypothesized distribution if the calculated value of test statistic is greater than chi-square critical value for alpha level of significance and with k minus p minus 1 degrees of freedom. Now this is important remark: for the goodness of fit test to work, all expected frequencies must be greater than or equal to 5. Some sources allow 3 and 4 also, but here we will consider that all the expected frequencies should be greater than or equal to 5 or at least 5. Now suppose some of the expected frequencies are less than 5, then we can combine them with adjacent categories. To achieve this, adjacent categories can be pooled. Suppose we find that expected frequencies for third and fourth category are say 2.3 and 3.7, then we can add these two and we can combine the categories corresponding to these two values of expected frequency which are less than 5. Okay, this we will discuss in detail when we solve the problems related to this goodness of fit test. The chi-square goodness of fit test is almost always right-tailed. So this is all about chi-square goodness of fit test. Again we just recall within a few minutes that we suppose we are given some population whose probability distribution is unknown. We don't know that which probability distribution is followed by given population. So to check that which distribution is followed by that population, we take a random sample of size n from that population. Now suppose that random sample is in terms of ungroup or row data. Suppose sample data is ungroup or row data, then first we arrange that data into different groups. So we will have groups and corresponding frequencies. These frequencies we will call as observed frequencies denoted by capital O. If our variable is discrete random variable, we will have integer values for these groups or categories or cells or bins. So here I will have different integer values and here I will have integers corresponding to particular frequency. So we are having values of variable or categories and corresponding frequencies. Now we will assume the null hypothesis that our population follows some particular distribution. Suppose our population follows Poisson distribution with some average number of events in particular interval. Suppose mean of Poisson distribution is lambda and it is known to us, and we want to test this null hypothesis. So we expect that our population follows Poisson distribution. So that means we can find out the probability that our distribution takes different categories. So we can find out that probability using the formula of probability mass function of that particular hypothesized population. Here I have assumed that X follows Poisson distribution, therefore I have written the probability mass function for Poisson distribution. And by multiplying these probabilities, these are called expected probabilities, and if we multiply these probabilities by total number of observations in the sample, we will obtain expected frequencies. And once we obtain expected frequencies, we will check that all the expected frequencies are at least 5 or greater than or equal to 5. After that, we will find out the value of test statistic, which is observed minus expected square divided by expected frequencies, and this test statistic is approximately following chi-square distribution with degrees of freedom equal to k minus p minus 1, where k is the number of categories or groups or cells, small p is the number of parameters of the hypothesized population which are estimated using sample data. For example, suppose here I don't know what is the parameter lambda of Poisson distribution, or suppose it is not given in the question, then I will estimate that parameter lambda using sample mean. So for that I will find out mean of this sample data. So I am using that sample mean as an estimator of population parameter lambda. So I will subtract the number of parameters which are estimated using sample data, that is small p in this formula, and minus 1. After that we find out critical value of chi-square corresponding to given level of significance and these degrees of freedom, and we remember that this chi-square distribution for this goodness of fit test has always right-tailed test, and therefore our rejection region will be in this right tail. Suppose this critical value is chi-square alpha comma degrees of freedom k minus p minus 1, then this area to the right side of this point is alpha, and this is the rejection region. So we check whether calculated value of test statistic is to the right side of this or if it is less than this, and accordingly we take the decision. If calculated value of test statistic is greater than this critical value chi-square alpha comma k minus p minus 1, then we reject the null hypothesis. So this is the idea of chi-square goodness of fit test, and in upcoming lectures we will discuss some questions related to this chi-square goodness of fit test. Thanks for